Okay, so I uploaded a new slide here, 4.3. This is an old slide, and I found today, this morning, there's lots of typo again. So I'll try, I'll try to review it again, and then I will follow some of the material here, but I'll try using my pad if there's so many typos. Okay, so so let's review about the quantum Fourier transform. So it's a unitary gate acting on n-qubit state. So n-qubit state is at base x cat, then it makes it into the superposed state of the following. So the common coefficient is 2 to the n over 2, and it sums over all the possible base states and with some special coefficient pi I x y times y. So x comes into here, and x and y inside of an exponent of exponential is simply an integer, not a binary expression, but just an integer. Now, let's try. So, and we discussed how to implement this QFT using control rotation and so on, and Hadamard, of course. So, we're going to make a circuit using QFT the following way. So, let's say I have a function from n binary digits to n binary digits. And then this is periodic. So which means that the number iterates over and over. So not the same number, but the sequence of values of functions are iterating over certain period. So I'm going to lay out the values in the domain. So here, let's say 0, 1, up to r minus 1, assuming r is our period. So this becomes f0 and f. So this f function f maps each 0 to r minus 1 to some value here. So you can imagine that this n bit of string is simply a number, represents a number less than 2 to the n. So these are all numbers between 0 to 2 to the n. So I'm going to just write it this way. So this is one period, and next period starts from here, from r plus 1 up to 2r minus 1. That's another period. So it repeats f0 and f1 and fr minus 1. Okay? So it goes forever. Not forever. Well, basically, it goes up to 2 to the n. Now, the question is, how do we find such period? Okay, so again, if we know the entire mapping of the function, you can just look the data to find out. But usually we have big number of n, so the number that we have to consider is huge. So we cannot get the entire sequence of functions from 0 to 2 to the n to check whether the period is what. So that's why basically Fourier transform is important, and now quantum Fourier transform gives another way of finding out the period. So let's make a circuit according to this. By the way, so our circuit requires the oracle like this. So y n. So input register and output register both goes into this oracle and doesn't change the input register, but the output register becomes y plus f of x. Okay. So here, now I'm using x and y, and also f of x as the binary representation of number. So that's why I made O plus instead of plus. Okay. So this is the oracle according to our defined function, and we don't know, basically, assumption is we don't know the function, but we have an oracle. Okay. So, so let's make a circuit like this. So we have 0 and we have 0. So top one is the input register, bottom one is the output register. Put it inside of big oracle, and then let's see. And then I take the quantum Fourier transform, FT, on the input register, and then I'm taking a measurement on output register, and then take a measurement in the input register. So I take the sequence of this operation so that we can compute by one, but in fact, you can combine the quantum Fourier transform with this measurement on the output register together, or you can combine measurements on input register and output register together. So it doesn't really matter, but I just made it in a sequential order. So let's try to compute at each step what the quantum states are. So in the beginning, it's size 0. So I'm going to label 0, 1, and 2, and 3. Well, here, there's no point of making a quantum quantum state after measuring any of these registers, but I'm gonna do it anyway. So after measuring the output register, I'll put it as 4 and 5. So here, it depends on the measurement. So the quantum state that I'm going to state on the state 4 and 5 depends on, sum assumes that certain measurement outcomes. So size 0 is simply 0 tensor 0. So let me make sure that the left one is the input register and the right one is the output. And psi 1, yes, psi 1 is after Hadamard. So even though I put Hadamard H1, but it means that I put Hadamard on every n registers in the input register. So that means I get 1 over 2 to the n over 2, sum over x from 0 to n minus 1, and just simply xn. And tensor with 1, 0. And then let's put that into the oracle. So it depends on the base state x, but it's superposed. So it becomes x0 to the n minus 1, xn, and adding to 0 becomes just f of x. Now what we do is sending the input register to quantum Fourier transform, size 3 into 2 to the n over 2, x from 0. So I'm going to write it in a long form so that everyone can follow the steps. So what happens here is you change it to 1 over 2 to the n minus over 2, y from 0 to 2 to the n, and exponential 2 to the n, 2 pi I, xy, and yn. Tensor f of x, n. Okay? So let's make it shorter. Combine 1 over 2 to the n over 2. It's 1 over 2 to the n. And we have x from 0 to 2 to the n, from y0 to the n minus 1 exponential 2 to the n to pi I x times y and yn. Okay, everyone okay with this? So far it's just applying definition. Now, what are we supposed to do next? We are supposed to measure the output register. So look at the output register right here. It's some number between 0 and 2 to the n, but it's periodic, right? So you pick numbers, then it fixes with that number. It's not number. If you measure the output register and you observe some state, then the output registers collapse to that state. So let's say I picked f of x to be, so the measurement outcome was L. Okay, so that's a number between 0 to 2 to the n based on the measurements on n register on the output register. So that's a measurement outcome. So L is in 0 to 2 to the n. So once again, let me make sure that this L is not measured, it's not obtained by one measurement. In fact, you have to take n measurement on every register, quantum register on the output register. So it consists of Ln minus 1, Ln minus 2, up to L0, where each Li is the measurement outcome of I's register, I's output register. Okay. So actually, it doesn't matter what the output is. The L doesn't really matter. What means that we want to fix all the input register, all the quantum information on the input register to a certain state where its value of function are the same. Okay. So by measuring the output register, we collapse all the input state into the superposed state of base state whose value are put it into the function. The value of function is the measurement outcome. Sorry. So once we have this, what was the number? 4. Psi 4 now becomes 1 over 2 to the, so everything collapses. So yn. So yeah, so what we have here is on the output state L, that's the measurement outcome. Because so actually, let me make sure that once you make an outcome, it's not, usually you don't state the quantum state anymore after the measurement, because the measurement means that you collapse, you ruin your information. But here I just state it as a Ln so that I can consist with this previous statement. So anyway, here what I'm assuming here is, okay, so among these all numbers of inputs from 0 to here up to 2 to the n minus 1, there are some number which is L, right? So let's see, let's say this is L, okay? So then this is also L, and here's another L, and so on, okay? So by taking a measurement, I can say x0 and x0 plus r and x0 plus 2r and so on. So maybe x0 plus mr are all mapped to L. And there could be more than x0 and more than one x0, right? So you may observe the number L once entire period, but the number L could appear twice in the sequence of the value of function. So you could have more than one choice of x0, but doesn't matter. So because just the superposed of those many x0s. So what I'm going to assume is there only one x0 that has a function value f of L when I compute the number between 0 to r minus 1. Okay? So in that case, how many? So I want this to be so m number of values. So I would make sure that m minus 1 times r. So how many values are how many states that I have after the measurement? Just m states, m base states are left here. So that they are x. So here. So x becomes these numbers. So we have 1 over square root of m. And now the question is, it's not x, but it's the index of coefficient of r that increase from 0 to m minus 1. Minus 1. And then what we are taking here is yeah, y n is here, but I'm gonna make this guy move a little bit here. So I'm gonna switch these to summation, x and y. So move y to the outer side, so 2 to the n. And the inside, because I don't see all the x's, I only see the x where f of x is L, and they're only, assuming that there are only m of them, so it's x of 2 to the n, 2 pi I need more space. So here, x is now x0 plus kr times y, and I need more space, and this. Okay. So, is everyone clear about this? So I have one assumption that our value L appears once in the period, so that I can pick only one x0 among 0 to 0 to r minus 1, whose function value is equal to n. So all I can see in the input state is x0, x0 plus r, x0 plus 2r, up to x0 plus m minus 1r. Only m of those give the function value L. Since I collapsed by measuring the output register, I collapsed the value of f of x to be L. All the input states are also collapsed. Okay. All right. So let's make it a little bit simpler. A little bit. Oh, since I think. Oh, sorry. So I cannot erase everything here. Since I only collapsed this part, that part becomes the coefficient of 1 over square root of m. But because of I didn't do anything on this summation, so I should leave this coefficient alone. So this is our new coefficient. So this is 1 over 2 to the n over 2 m. And then let's see. So here I can split this exponential into x of 2 to the n 2 pi I x0 y times x of 2 to the n 2 pi I r y k. Let's make it this way. Okay, so the first part, this one is independent of k, so I can move this outside here, x of 2 to the n 2 pi I x0 y, and then make another sum for k 0 to n minus 1 and x of 2 to the n 2 pi I r y k. Okay, so n y. So actually the y is here, and then tensor L. So at this moment, it really doesn't matter what output register is, because we already collapsed it to L base state, so we can erase it, but I'm just leaving it so that it matches the format of the previous state. Now, what we're going to do is met the what's the next step. So after making a measurement on output register, so at the step 5, we make measurement on input register. So let's say the measurement, oh, I already used M, so N, I cannot use N. Let X, let's say mu be the output as measurement outcome of the input register. Okay, so that means entire state right here, all the y, the superposition of y, all possible y, are collapsed into mu state, mu cat. Okay, so let's write psi 5. So it becomes 1 over 2 to the, so it should, now in the process, so this coefficient is now going to vanish because we made a measurement. So it's going to collapse, just the entire summation becomes 1 cat state, and that disappears. What we are left with is 1 over square root of m exponential 2 to the n 2 pi I x0 y, and then sum over k from 0 to n minus 1. So exponential 2 to the n 2 pi I r. Now y is mu, so r mu k and mu tensor L. Okay. So what do we care about here? Well, we care about what does that information of measurement outcome means. So overall, what we did is, without knowing anything about the oracle, we just got the result from measurement on input register and output registers as mu and L. So as I said, L doesn't matter. What actually matters is mu. What kind of information? So our question is, what kind of information can we derive from the measurement outcome of input register? Information can be derived from the measurement outcome. Okay, well, the second thought, maybe the measurement outcome of output register also matters, because when you see what we're going to talk about soon, then you will see that it's a little bit difference between what measurement outcome of L is. So anyway, let's take a probability. So this is the statement, and this is the quantum state after making all the measurement. Okay. By the way, if we could done this many times, what is the probability of observing this mu and L on input and output register? That is the square the square of the coefficient, square of the absolute value of this coefficient, right? So let's compute this. So the probability of observing the mu and L on the input and output register is, okay, 1 over m, and absolute value 2 to the n 2 pi I x0 y square root. So that's the first factor. Okay, so it's kind of misleading, but actually, this is actually wrong, because I have to admit that when I say psi 5 is this, it's wrong, because whenever I take a measurement, this whole thing is just vanished. So this coefficient vanishes when you take the measurement. Once you take the measurement, the quantum state collapses into this. But I left this coefficient just to show you that before you take a measurement, this was the coefficient of this cat state. Okay. So when I say this is the quantum state after measurement, technically, I mean, theoretically, it's wrong. Okay, that's wrong. But I just want to leave it here so that make the formula easy to read. Okay, so make sure that this is theoretically it's wrong. Oh, it's wrong. Okay, but anyway, so let's compute the coefficient, the square of the absolute value of this coefficient. That's about to erase. So here we have 2 to the n 2 pi I r mu k square. All right, now it gets interesting. So what's the 1 over m is just a number, and what's the next number? It's x pop something, and with the imaginary number inside. So with the Euler formula, it's cosine plus sine. So basically, if you take the size of that, it's a complex number. So the size of this complex number is always 1, because it always lies in a unit circle. Okay. So I'm going to introduce again the x of theta I is cosine theta sine theta, and this has the size 1, so it just becomes 1 here. And how about this part? So it's basically the geometric series, finite geometric series. The common ratio is x of this, not except k. So this is 1 minus x of 2 to the n 2 pi I r mu over 1 minus x of 2 to the n 2 pi I r mu m, right? So that's the number. Okay. Well, here's one fact that we can check. What if, so if this R mu here, right here. Not mu, sorry. So I should change this a little bit here. So let's write it Rm mu here. So what if this R and M is integer multiple of 2 to the power of n? So if this Rm is, let's say, some multiple, a times 2 to the n. Well, actually, a is 1, basically, because r is the period and m is the number of iteration of that period. So you cannot have more than one as a. So anyway, if that happens, and a is an integer, then what really happens is the numerator, the exponential in the numerator becomes 0, right? So if Rm right here is the integer multiple of 2 to the power of n, then this whole thing is integer multiple of 2 pi I, right? So mu is integer, and Rm over 2 to the n is integer. So it's 2 pi I times integer inside exponential, and that makes, using the Euler formula, the whole exponential becomes 1. This whole exponential becomes 1, and 1 minus 1 is obviously 0, so everything vanishes. So when does it happen? So by the way, so finish this line, then this whole thing is 0. So when does it happen? What does it mean that we have r times n equals to multiple of 2 to the n? That means our period r is 2 to the n, and m is simply the number of iterations, so that's all. So this means this happens that r divides 2 to the n. So when I put the bar in between two numbers, left one divides the right one. Sometimes in other literature they reverse the order, but let's decide that whenever I write that way, it means r divides 2 to the n. Okay, so left one divides the right one. It will appear many times when we discuss the number theory part. It happens when this happens. So as you can see, this is not always happening. So you can have a period r, not an integer, not a power of 2, right? So you can have any period. Well, actually, it has to be less than 2 to the n minus 1, because at least if you want to know the period is this, then you need to have at least twice of that period going on. So the maximum number of period that you can observe or you can detect in the length of 2 to the n is 2 to the n minus 1. But in between 1 to 2 to the n minus 1, you can have any number of period for your function, right? So this is a rare chance that this r, the period, could divide 2 to the n, because there are finitely many and many cases for such number. So that doesn't really happen much. By the way, well, then what happens when that doesn't happen? So let's compute this probability further. So let's try to compute what this is first. So let's try to compute this, because when you compute the complex number like this, it's the square root of absolute value on the numerator divided by square of the absolute value on the denominator. So I can split the I can distribute the square of the absolute value on top and bottom. So generally that's the form of 1 minus x of theta I squared. So that means we have 1 minus cosine theta plus I sine theta squared. So this is what? 1 minus cosine theta minus I sine theta squared. So how do you take the size of a vector squared? So just take the conjugate complex number and then multiply it together. So it's 1 minus cosine theta minus I sine theta, and then 1 minus cosine theta plus sine theta. So it's 1 minus cosine theta square plus sine square. So when we split it into summations, we have cosine and cosine square, sine square, and we have 2 minus 2 sine theta, and this is 1 minus, I can rewrite it as theta over 2 plus theta over 2. So, well, you know the formula for the sum of cosine. So it's 2 times theta over 2. So it's 2 of, what was it? So let me do it in a longer form. So we have cosine square sine square minus, so this one is what? Cosine square 2 theta minus sine square, right? So it's a formula of cosine sum, right? So we have canceling of cosine and we have double of sine. Actually, it's 4, so it's a 4 times sine square theta over 2. Okay, so this can be simply written in this form. So I'm going to plug that in here. So 1 over m times 4 times, and also we have square, so it's fine. So we have sine square. So 1 over 2. What was the theta? We have 2 to the n. 2 pi, no I anymore, and r mu. Okay, and then on the top we have sine square 1 over 2, 2 pi r mu. What was the last one? M right here, m 2 to the n. Okay, so basically 1 over m times sine square 1 over 2 to the n 2 pi r mu sine square 1 over 2 to the n 2 pi r mu n. Okay. Now, so that's that. That's the probability. And well, once you have the measurement outcome of mu on the input register, you can guess that that outcome was indeed obtained with this probability. Okay. Now, our goal is to find the period. Again, our goal is to use quantum Fourier transform to find the period of function. But we cannot just randomly query the quantum oracle. We need a certain plan so that we can do it efficiently. So let me state the goal first. Goal is to find R using the QFT circuit. Okay. So what we're going to assume is that we are going to take the measurement until we have certain form of measurement outcome. So, which is saying that we're going to keep query the quantum circuit just we laid out before until you get a specific form of mu. So what is that? So we're going to, so let me state that clearly here. So take measurement until we get mu of this form. So not any mu, we're going to say r to the 2 to the n times some j plus delta here, j here. So where delta j is 1 over 2. So I want to take the measurement so that my mu, the measurement outcome, is in the delta j error distance from this number right here. Okay, 2 to the n over r times some integer. So here j is an integer. That's a strange number, but let me give an example what that really means. So let's see, I have, let's say, n equals to 5 and r equals to 3, or maybe 3 is too small. Maybe 7, maybe? Okay. So then 2 to the 5 over 7 is based, how much is it? So let's take 3, okay? So that means, how much is it? 32 times 3 over 7, it's 96 over 7, so it's 1 is mu 3 or 0.7 something, right? So if I choose mu equals to 14, then my mu and this number has an error distance less than 1 over 2, because 14 minus 13.7 is less than 0.5. Okay, so it's possible to find such mu, right? So I'm saying that there is such mu that satisfies this equality or condition, okay? And let's count in what probability we could measure such mu. Okay, so I'm going to plug that in as if I got this number already, and let's put that put this formula of mu right here into here, right in this place, and actually compute the probability together. So so the probability is 1 over m times, so it's a long computation, so I may take a lot of spaces here. So it's 1 over 2, 2 to the n, 2 pi, and r times 2 to the n over r times j plus delta j. So here, delta j really doesn't matter. Here, don't put too much meaning to the index j on delta. It's just to differentiate each j's here. So because j could run through 0 to r minus 1, right? So you could have j equals to r, but that's reduces the chances to have your mu satisfies this equation almost equal to 0, because your mu has to be almost equal to 2 to the n. So anyway, j only runs from 0 to r minus 1. So for each j, I'm assuming that my error delta is delta j. Okay, don't put too much meaning to the index here. So, and then above here we have 1 over 2, 2 pi, 2 to the n, r m times r to n j plus delta j. Okay, that was the probability. And let's see. Let me make it simpler. We have sine square 1 over 2. So we have this cancels out. So r to n cancels out. So 2 pi j plus and 2n 2 pi r delta j, right? And on the numerator, we have sine square. And we also have canceling out rn to the power of n. And we have 2 pi mj. And what do we have? Plus 2 to the n 2 pi r m delta j. Okay. So we're making another assumption that our number 2 to the n is a quite big number, and our period compared to the 2 to the n, period r is comparatively small. So your r times n, r times m. So this is how far you can make a whole period inside of your entire number up to 2 to the n. From Rm, where Rm plus 1 up until 2 to the n minus 1, your period starts but it doesn't finish because it doesn't have R number of elements here. But since we're assuming that R, the period, is comparatively smaller than the entire series, the entire number, this remaining part can be negligible, ignorable. So you can just this numbers, the number of these remaining part is comparatively like 0. Okay, so it doesn't really count. So you can say that this Rm is almost equal to R2 to the n. So you can say this is almost equals to 1. The ratio of Rm and 2 to the n is almost equals to 1. And you can say that also R over 2 to the n is almost equals to 0, but not 0, of course. So it's not, maybe it's not a good way to write this. So it's way smaller than 1. So it's if you're a computer major, then you've probably seen this symbol before. So it means that it's very small number, but you can't count it as a 0. Still, it's very close to 0, but that means that let's not ignore the size. Okay. So you can, since we are taking squares here, you can ignore this part. It only changes the sign, the plus and minus of the sign function. And what matters is this part, the remaining part here. So it's 1 over m and sine square. And here, as I said, since this one right here, r over 2 to the n, is very small number, what happens when you plug in the small number close to 0 into the function of sine? Sine behaves as if it's a y equals to x function when x is almost equals to 0, close to 0. So you can ignore the value of sine and just consider this is just that number. So instead of sine, now we need to use approximation, not equal. It's approximately. So ignore sine from now on. Just take 1 over 2 and this 2 to the n 2 pi r delta j squared. So it's not an absolute value anymore. It's just a square because it's a real number. And how about the upper part? So in the upper part, as I said, it's simply 1. So this part, this Rm over 2 to the n is almost 1, right? And this delta J is, so we can just ignore this. So it's just the 1. So I can just write it as sine square of 1 over 2. Let's combine delta J right here, and then 2 pi, and that's it. Okay. All right. Oh, and maybe I can make it a little bit better. So it's just delta J pi, right? Because everything vanishes. So, yeah. So let's make it computation again. We have what? 2 m here and 4 and times 2 to the 2n. So I think I should put 2 to the 2n somewhere. So anyway, well, let's fix it later. So, and then 2 pi r square, and we have delta j square. So that's after moving this everything on the denominator over outside of the ratio, and we have sine square delta j pi. Okay. Yeah. Oh, okay, yes. And then we have this assumption. So I'm gonna make this part a little bit simpler. So what I'm gonna do is we have 2n over rm squared taken up outside, and then we have 2 pi square, or just collect all the remaining part, and we have to make m times, and that's all, right? So we have m over delta j square. So basically I can combine like this. So we have m and then sine delta j pi over delta j square. Okay. So what happened to this part? I said it's almost equals to 1, so I can ignore this. So this is almost equals to 1 over, so it's m over pi square sine delta j pi delta j. Okay. There's some mistake in here because actually what we have to get is not having m over here. I need something like this. I shouldn't get this big number because m, if m is on the numerator, it's too big. And let's see, let me check if I got everything right. So maybe it's a good time to just look up the formula if I have one here. Let's see. Let's see if I have. Here. Yeah, that's what I'm saying. So I need r on denominator. So I see. I think I need to keep this 2 to the n. So yep, so I need this 2 to the n in the beginning. So let's go back here. So I think I made mistake in here when computing the probability here. So Okay, that's what I'm worried uh, when I state the quantum state after the measurement, because after the measurement, everything collapses and you lose all the information about coefficient. But here, what we're trying to compute is the probability, not before and not after you make the measurement, before you take the measurement. So computing the probability after you make the measurement, it doesn't make sense. So that's what I was worried about when I do this. Okay, so yeah, so okay, so we have to start from here. Now we made the measurement here. We made the measurement uh, at this point. So after making measurement on the output register, it's okay to collapse the output register. That's what we actually intended. But just before we make a measurement on the input register, I want to compute the probability of observing some number, say mu. Okay, so that's what I want to compute, the probability. So I want to find the coefficient when this y cat is the mu cat. Okay, so that case, I cannot forget this 1 over 2 to the n over 2, because that's there in the superposition of everything. I cannot collapse this, because if I want to compute the probability, I cannot assume that its state is collapsed already. So I keep that 2 to the n. And yeah, so when I take the probability as a square, I get 2 to the n right here and 2 to the n right here. And there's something I should want to check again. Okay. So here, when I said that, okay, 2 minus 2 times cosine theta, 1 over 1 minus this, and then cosine, 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 cosine. Isn't there a 1 over 2 someplace when you have a cosine sum? Did I do computation here correct? Okay, but it doesn't change the result. So, but I just want to make sure that I did this correct. So, okay, so let's skip this one. And okay, so we have, yeah, so we have this, and now we put this, and so we have 2 to the n, 2 to the n here, and now we have 2 to the n. We get 2 to the n, and now we have 2 to the n. So now, my computation gets a little bit different, so I can cancel this with this 2 up here, and then I can combine 2 to the n remaining on up here with mr, 1m, 1r here, and I still have r left at the bottom, and not m. I don't have any m here. So that's all, right? So yeah, so then I get 4 canceled out and 1 over r, and pi can be go inside the parenthesis. So that's what I got. Okay. Now we can think about what is this. So we assume that, our assumption is delta j has absolute value less than 1 over 2, right? So let's draw a picture of sine x over x when x is minus 1 over 2 to minus just 1 over 2. So I think derived from simple curve like this one. So this is pi over 2, that's just shape of sine. And so it's okay, so if you take this line, y equals to x, then sine x is always less than x when x is in between 0 and 1 over 2, right? So when you take so when you take x, not 1 over 2, pi over 2. So when you take this, then it's 1 over less than 1. Less than 1 is not good. I want the lower bound, not the upper bound. Sorry. So I want the lower bound. Let me check this again. So, right. So what I want is sine x. So here, what I want is sine x pi is bigger than this pi 2 over pi. So I want this inequality. Oh, okay. Yes. That not looking at the tangent line. I have to look at this line. I have to look at this line. These lines. So actually, this one on the positive side. So this line is y pi over 2x, right? So when your x is in between 0 to pi over 2, this yellow line is always below the sine curve, right? So I can say that this inequality, let's erase this one, erase everything here. So we have sine x is less than pi over 2x when x is in between 0 to pi over 2. So sine x over x is less than 2 over pi. So when you take the square root, it's 4 over pi squared. So, no, the opposite. Sorry. The inequality is opposite. So sine is bigger than this. So now I have this one. Okay, when x is in between this, so just square root here. It doesn't matter whether x is negative because it can always consider it as a positive. So we have inequality, and we can plug that here because delta j is in between 0 and 1 over 2. So this one is bigger than pi squared times r4. Okay, so this is our lower bound of our probability. So what is the probability again? So this is the probability of observing the mu, the output, the measurement outcome of input register when the mu has an error between 2 to the power of n over r with less than 1 over 2. So when the mu is of this form. Okay, so it's complicated, but let me state again. So we computed the probability of observing mu of this form in specific j. Okay, so we didn't specify what j is, but assuming that we have one particular number j between 0 and r over 1, r minus 1, we have this minimum probability of having such number. Now, the question is, it doesn't matter what j is. j could be any number between 0 and r minus 1. So what is the probability of getting the output measurement outcome of the input register of this form, no matter what j is? It's the sum of all this probability. So let me state it here. The probability of observing the input register as mu in the following form is at least r times what? This much. R times 4 over r times pi over 2. That means 4 over pi over 2. And I forgot the exact number, but I think it's bigger than 40. So it's bigger than 40%. So mu is 2n over r times j plus delta j for some j from 0 to r minus 1. Okay? That's the conclusion right here so far. So we made a quantum circuit using QFT and quantum oracle. Imagine that there is some quantum oracle that we want to find out about the function, and we passed the information and measured and got the measurement outcome. And it says at least more than every time you make a measurement, more than 40% chances that you measure your measurement outcome from the input register is of the form of this, that your number is in less than 1/2 distance from this number, 2 to the n over r times j. Okay? So why is it important? So it's important because the number theory that we're going to cover next time says if you have such information, you can find out with probability what the r and j is. So what we do know here is that we know mu, that's the measurement outcome. We know 2 to the n, the number n here, but we don't know what r and j is, right? Actually, the number j doesn't matter. What we want to know is r, but let's make this equation a little bit different form. So I'm going to say this is mu minus r 2n times j, and this is delta j, and we know that this is less than 1 over 2. So I'm going to divide 2 to the n on left and right. So what we get is 2 to the n mu minus r j and less than 1 over 2. Okay, so look at this inequality. We know this. This is what we know. Okay, after measurement. But we don't know this. But we know some information about R. We know absolutely, and also J. We know that J is less than R, so J over R is less than 1. And also know that R is somehow in between of 0 and 2 to the n, or 2 to the n minus 1. And so, and also they are integers. But with that information, what we can do is using forgot the name. A continued fraction. So there's the thing called the continuous fraction to represent a rational number, and the theory of continued fraction says if you have such inequality, then you can find, or you can approximate your r and j in a, oh sorry, I forgot this, 2 to the power of not just 1 over 2, it's 2 to the power of n over n plus 1. So if you have such inequality between continued fraction, you can find out what the rational number that this continued fraction represent if the error between these two numbers are less than certain number here. So we're gonna learn how to use continued fraction to find out what J over R is. So let me finish it by writing this. Using continued fraction, we can find J over R, satisfying that J is less than, okay, so J is less than R, and R cannot be 0, so it's less than 2. Okay, so that's really crucial. Of course, if you don't have any information about R and J or the range of R and J, there's no way you can find what J and R is. You cannot at least fix one number. I mean, there are infinite things, but if you have certain condition like this too, that R is less than this, then you can always find, you can uniquely identify what J over R is. Okay, so it's here, unique J over R, yes. What is it? Okay, so today I tried to cover as much as I could, but I don't want to go further from here. What we need to talk about from now on is to, well, of course, the continued fraction to explain why or how we can find out J over R, and also how does finding the period help the code breaking, or at least the reason why you are learning about why Shor's algorithm is so important. How could this period finding circuit help us to, motivate our learning of quantum computing? So we need to talk about how this RSA inscription works, and that also requires some number theory, and not really hard number theory compared to the continued fraction. So we should talk about that, and then that closes the Shor's algorithm. But before we finish our class, I want, if there anyone have a question, then I want to spend time to answer that. So let me know if you have any question so far. By the way, I'm gonna upload my note, so don't worry about writing down everything right now. So you can find out the details later after I upload my note, but you have to get the general idea what the logics are. So we want to find the period of a function that maps n-bit string to n-bit string. So basically, it's a mapping between two natural numbers, set of natural numbers. Okay. And as I said, it's not free. It's not like a previous algorithm that we discussed. So you have to pass the quantum circuit, but doesn't guarantee 100% that you get the period, because we can get the period only when you get the mu satisfying certain condition, like this one. And that is not 100% guaranteed, but there is a big chance, like bigger than 40%, the 40% is quite big, and you have a big chance to get such type of number as a measurement outcome. So it's a very good strategy to implement. So, so here you could have a question. So you don't have guarantee that when you get the measurement outcome, whether your number mu is in this form. Okay, that's a catch. So you have at least 40% chance to get such mu like this one, but in practice, once you get the measurement outcome, you can't decide whether your number mu fall into this type or not. So you have to assume that whatever you got as a measurement outcome is of this form, and keep doing the process to find the period R. Okay. However, if the actual mu is not actually of this form, you will get the wrong answer for the period. Okay, but the catch is we're not gonna get the period by one measurement. So we're gonna repeat this measurement again and again and find the period, or can't find the candidate of the period again and again, so that if you found the period, it's easy to see, easy to check whether that's the real period. Because you see, the entire series of 0 to 2 to the n is quite long, so you cannot actually query all the numbers here, right? If n is 100, like too many, right? It takes too much time. But let's say you have you have a candidate of your period such as 30. You can just query from anywhere that 30 number from there, whether the next 30 is repeating, and so on. So once you have a period, it's easy to check whether that's actually period. So that's, so you see what happening. So once you have measured your outcome and you guessed what so you can logically derive what could be the period, assuming that this is right mu, the right format. But you could get wrong, but then you can check whether your period, your answer is actually right. And if it's not, then you can do it again and again until you find the actual period. So suppose that your checking process guarantees 100% whether your period is right or not, then like you have more than 40% chance to get the right period every time you take the measurement. So if you take 10 times the measurement, it's hard to get all the 10 answers incorrect, right? Yeah, at most 4/10 times the 10th power chances to get everything wrong. That's how it works. So if you have any question, let me know. We'll talk about the continuous fraction next time. So we'll see on Friday.